So a bit of context about the talk before I sort of introduce myself. I was recently given the opportunity to have what's called like a learning day where I work, and they said, right, go off and research a technology or learn about a technology that you might not otherwise learn about, and then come back and report on it. And this is kind of where I sort of picked up this knowledge that I'm wanting to share today. So I'm not an expert in this, but in this topic, but it's a really good introduction, I think, I put together, and a really good stepping off point if it's something you wanted to look at further. So today we're going to look at how we can use Unity and a simulator to see if we can create self-learning and self-driving two-dimensional cars. Right, who am I though? So my name is Lee Englestone, as the team said. I'm currently DevRel, Developer Relations Lead at Avanade. So Avanade is probably the largest company you've never heard of. We're a global IT consultancy, and we specialize in Microsoft Stack. And we're actually formed by Microsoft and Accenture 20 years ago. And believe it or not, there's about 40,000 of us around the world. Yeah, that's Avanade. I'm also a Microsoft MVP in developer technologies, have been for a couple of years now. I like to put some websites together that help other developers, things like visualstudiotips.co.uk, and most recently one called techcommunitycalendar.com, which aggregates tech events, meetups, hackathons, and call for papers and speakers as well. So check that out if you're interested in the tech community and tech events. And also I have a published book on augmented reality for .NET developers, if you want to experiment with creating augmented reality experiences for iOS devices. So a bit of bedtime reading there if you're into that sort of thing. Okay, really quick slide about Avanade. We are hiring. We've got loads of great reasons to work here. If you are looking to move or thinking about moving, please, come and approach me after the talk or some other time. Just reach out to me. I'm happy to talk about this sort of stuff. So that's Avanade. Yeah. Right. Okay. The actual talk itself. So my motivation for wanting to sort of learn this sort of technology, this artificial intelligence, or using artificial intelligence to create sort of self-driving cars via simulation. So a few years ago now, I found a video on YouTube, and the links at the bottom. Don't click it now, click it later. And what the developer had done is that they'd created a car that knew only about the distance from itself and the sides of this track, and how the distance in front of it and the speed it was going. And he claimed to be able to get it to spawn future generations of cars after it crashed and teach them how to better navigate the course. And sure enough, by the end of the video, he had cars flying around this course at breakneck speeds, or not crashing into the sides after earlier generations had crashed. And I thought this was amazing. This was back in 2019. And I wasn't the only one. It has today about 3.5 million views and 60,000 likes. But unfortunately, the person chose not to share the source code, so I couldn't learn from it. But I since found a very similar source code, and that's what we're going to look at today. And this person in this video talks about neural networks and how he uses it to pass learning to future generations. Slightly different to this topic. He was actually choosing the cars by clicking on them, which he wanted to pass the knowledge on to future generations. The stuff we're going to look at, we automatically determine which cars are best fit to spawn future generations. Okay, but before we look at the software, I want to talk about biology, because neural networks and the way they're implemented, they kind of take the inspiration from the way our brains work. And so it's probably worth talking just a couple of slides about that. So in our brains, we have these things called neurons, and between them, we have synapses, and the neurons are connected by these things called dendrites. And the more important thing you've got to remember is that when we perform a task, we have these pathways between these neurons are firing. And the way we learn is that for when you're learning a bike or something like that, you need to be able to realize that you need to balance, steer, pedal, look where you're going all at the same time. And we only do that because we have pathways that are firing for our brains, and the more that we practice, they fire more repeatedly, and that link gets stronger, and that's how we learn things. Very, very basic biology. Probably not explained it very well. So these are what they look like under the microscope. They're very, very small, but we have billions of them. Each human brain has about 100 billion of them, and you can see under the microscope the kind of fleshy neuron bit and the dendrites coming off, connecting with other neurons. It will become apparent why I'm talking about neurons in the brain shortly. So that's biology. Also got to think about psychology, because this is where we get this concept of reinforcement learning from. So I don't know if you've got a pet or possibly a child, and what you want to do more often than not is reward and encourage good behavior and discourage bad behavior. So if you look at the sides, you can see I've got a dog, and maybe we say to this dog, sit, and then if it sits, we reward it with a treat, and that dog knows if we say sit, it will get a treat, so that it knows, it forms that connection, that reinforcement learning to encourage that good behavior. And conversely, if we want to discourage a dog, for example, chewing our shoe, like you can see in the slide, then if you squirt it with a water pistol, I've never done this, by the way, or squirted a child with a water pistol to punish them. If we want to discourage that behavior, because we don't want it to happen so frequently, that child or dog will learn, if I do this bad behavior, I will get punished, so I should do less of it. So that's reinforcement learning in a nutshell. And we can represent that reinforcement learning in this sort of systematic diagram, where we have this learning agent, which could be a child or a dog or an AI simulation car, we're going to look at today. And we perform an action on our environment, and then we give it feedback either with a reward or punishment, depending on whether we want to encourage more of this behavior or discourage this behavior. And then that updates the internal state of this learning agent. Effectively, it knows, right, okay, if I perform this action in future, something good will happen or something bad will happen. And this is what we're interested in kind of replicating in this simulation as well. And that is how Google Mind's Agent 57, which is a machine learning agent, they managed to train this learning agent to complete all 57 Atari 2600 games. And if you think about it, it's quite remarkable, because the very, very few limited inputs in an Atari, this Atari joystick, you've got one button and a number of sort of directions. And the way they trained this learning agent was they kind of fed back with reinforcement learning whether what it was doing was good, i.e. you got to the end of the level, or you completed the game, or it was bad, like you lost a life, or you got hit by a projectile, or you crashed into a wall, or you fell down a hole. And using neural networks and this reinforcement learning, they were able to create this Agent 57 and have it complete these games. And not only that, they would perform them better than on average than a human. And it's worth just mentioning that the logic wasn't put in there to tell the learning agent, jump over this hole, dodge this bullet. What it's doing is it was saying, based on the inputs you've given, we're happy or not happy with these outputs. And then it was updating this neural network. And we'll talk about that a little bit more in future. Okay, so again, a bit more on neural networks. They can be a little bit of a tricky topic to describe. So I've got a bit of a contrived analogy to give you. If you've ever played Guess Who, and I'm hoping a few of you on the call have. The whole idea is that you have a selection of faces, your opponent has a selection of faces, and you choose a face that your opponent has to guess, and your opponent has got a face that you have to guess, and you have to ask a series of questions to arrive to get closer and closer to the answer. So if you can say, does your person have a hat? And they say, yes, they do have a hat. You can flip down all the people that don't have a hat, and you're sort of slowly narrowing in on what you're trying to achieve. So if you think of a neural network as you've got a number of inputs, and as you go through this neural network, or these neurons, which are connected by these dendrites, these pathways, as you go through the layers, you're getting closer to the end result. Now, in in reality, these neural networks are just weighted pathways and things called activation functions, and they're just represented by numbers under the hood. And I'm not going to talk about the maths, but just to bear that in mind as well. I do actually have a separate talk, which I do train a machine learning model, an image classification model, which is very similar concept. So I actually trained an image classification model using a neural network to identify whether a cartoon character or an image of a cartoon character is a good cartoon character or a bad one. If you go to goodyourbaddie.com, you can play around with this for yourself. And what it's actually doing is it's training these neural networks so that if you give it certain images, it will input that image through the left-hand side of the neural network. In the input layer, it will go through the hidden layers, which are hidden for a very good reason. We don't need to know about them. And based on the weighted pathways, it will take a different path through the hidden layers and arrive out at a different output layer, have a different result. Quite hard to describe, but that's kind of it's probably as much I want to talk about neural networks right now. Okay, so then going back to the actual talk, the question that we're asking ourselves is, can cars teach themselves to navigate a track using neural networks, reinforcement learnings, and what does GS stand for? Genetic algorithms. So, and if so, how? So that's what we're going to look at today. And more accurately, we're going to run a simulation that was not created by myself or the code, but by someone called John David Anthony. So I've got a link to his GitHub repo here. And I've spoken with John, and he was more than happy for me to share his code and talk about his work and his project. And if one of the few things you do after this talk is I suggest you pull down John's GitHub repo and run it locally via Unity, and you'll just be able to run this simulation and you'll be able to see, play around with it yourselves. So on to the simulation. Our learning agents are going to be our cars on this track. And each car only knows about 6 different things, 6 different inputs. Okay, it only knows about the difference between the walls to its left and right, in front and at 45 degrees, and the speed it's going. That's the only things it's aware of. And each car has its own neural network, which is actually randomly generated every time a new car is spawned. So each car has got a different neural network to each other car, and we'll talk about that why in a minute. So when this simulation starts, we hit play in Unity, it will spawn 25 cars at a time. And then what you'll see happen is pretty much immediately, the cars all crash into the walls almost immediately. But some of the cars will get further than others. And it's those cars that we're interested in knowing how they got further than the others. We're not bothered about the ones that crashed in the car. We're interested about the ones that got further. And over time, as it spawns more generations of cars, what the coding is doing, it's passing that learning from those more successful cars into future generations so that they can better navigate the course. And we'll see how that works in a minute. Some other things to mention about the simulation is that you can speed it up. So you can increase the time scale. So you can speed up to 10, 20 times speed, because otherwise it can take a few generations for these cars to start progressing around this track and starting to learn. So you really do want to speed that up. And the other thing to mention is you can actually see a representation of the leading car's neural network, the input neurons, the input layer, the neurons in the input layer on the left, the hidden layer in the middle, and the output layers on the right, which we will look at next. Yes. So as I mentioned, every car has got a different neural network, which is randomly generated. And what's randomly generated are actually the weightings between the neurons. And what that means is each car, if it's given the same inputs, has the same distances from the sides and the same speed into the input layer, there actually is a mathematical transform that happens, or this activation function through the hidden layer, and actually will result in a different output value, which will mean it will turn left to a different degree, or it will go forward or reverse to a different degree. And And that's why these neural networks are randomized for our scenario. It just means every car will perform differently initially. Okay, so that's neural networks. And just to prove that we're not explicitly coding any logic in here, if I was to look at a successful car that managed to navigate around the track without crashing eventually, this is what its brain looks like. You can see it's got the number of input layers, the number of neurons in the hidden layer, and the number of output neurons in the output layer. And those output ones are just left and right and forwards and backwards. And all these other numbers are just the weightings between the neurons. So if I was to take that brain of that text file and input into a new car on the track, it would immediately be able to navigate the course, because it knows that if it's getting close to the walls, it's going to run those inputs through the weighted pathways, and it's going to apply these multiplications, and it's going to result in the correct turning away from the wall. I don't know how to describe. I just want to quickly mention why I talked about biology at the beginning. Now, in John's code, he's actually taken these concepts of biology and the brain, and he's input them into his code. So he's got this neuron class, which has got a list or a collection of dendrites, which is the connection between the neurons, if you remember correctly. And then each dendrite has got this weighting, which is like this ability to, this multiplication factor, whether to apply a positive or negative multiplication factor, that in turn affects the output values. So yeah, interesting code. Okay, so we've talked about the learning agents, and we've talked about some of these cars are going to perform better than others. We need a way of measuring how successful some of these cars are than others. And we do this using a fitness function. And the fitness function, and apologies for the spelling mistake down at the bottom, calculate. The way that John's done this is that he has calculated the overall fitness of the cars as the distance traveled, the speed it was going, the average speed it was going, and how well it was able to stay in the middle of the lane. You'll also see a multiplier in there in case we wanted to give more weighting to a particular factor. So if we thought speed was more important than distance travel, we can increase that multiplier from its default, which is 1. This fitness also means that if two cars traveled the same distance, but one did it faster, then we'll say that one's fitter. Or if two cars traveled the same speed at the same distance, but one managed to stay close to the middle of the road, then we'll calculate that one as being more fit. And the reason that we're interested in this fitness is that we've got to think about survival of the fittest, because we're only interested in the traits or the values of these, the fittest learning agents and the values in its neural network, because they're the only ones really we want to pass on to the next generation of spawned learning agents, as in this slide. So it kind of loops over and over like this until it finds a car that successfully navigates the course. And this is where this sort of a genetic algorithm sort of comes in. So it spawns a generation of cars, and I mentioned that each one has got a random neural network with random weightings and will perform differently. Each one will crash. They all crash, and at the beginning anyway. And once we've done that, we can say how fit, or calculate the fitness of each car and order them by the fittest at the top and the not so fit at the bottom. And we take the top 2 cars that perform the best, and we effectively use them as the parents of the future generation cars, and we get them to kind of mate. So it takes, and in John's logic, what he's done is he's taken some of the traits from one of the parents and some of the traits from the other parent and combine them into the traits of their children. And it's worth mentioning that similar to normal genetics, you don't get all of your, I think this is right, you don't get all of the genes from your dad, and you don't get all your genes from your mum. You get a selection from the both of them. It's also, what John's also done is, once he's sort of bred these new children, is implemented a kind of mutation factor. And what that means is that the children aren't necessarily limited to the traits it's inherited from its parents. It allows this slight chance, and you can tweak this in his code, it's quite clever, the slight chance of improvements creeping in, just like in normal genetics. You know, you might have a random mutation in your genes that neither your parents have, and you maybe might have, you know, a genetic defect, or you know, you might be able to run faster than both your parents. I don't know. I'm not a geneticist. That much is probably apparent. So this is kind of what's happening over and over again until we have several generations of cars. We have cars that can go all the way around the course, and it looks a bit like this, the evolution, if you kind of speed it up. So in generation 1, the cars don't get very far. I'm really hoping the video is playing now. If not, I don't know what we're going to do. I'll just describe it. In generation 1, the cars aren't getting very far. They're not even getting around the first bend, and you can see this as it's played through Unity. Now, it takes up to generation 32 for the cars to actually get around the first bend. And as you can see, as the generations progress, a larger number of cars are actually being more successful. And it takes until generation 128 for the first car to start making it all the way around the track. And this isn't necessarily always linear. I run the simulation sometimes, and it only takes until generation 58 to get away around the track. Sometimes it takes generation over 200 to get all the way around the track. But it does learn how to make it around the track. And not only that, you'll see probably, hopefully in this video, that not only does it get around the track, there's some learned behavior that creeps in that we're not explicitly telling it to do. It seems to slow down as it approaches a corner. Again, we're not explicitly telling it to do that. It's arrived at that conclusion because future successful ancestors have had this trait. So it's kind of inherited that based on the input sensors and the speed and the weighted functions, and there's weighted pathways and the output variables. Yeah, so it is, again, I just want to hammer home the fact we've now got a car that can navigate that track, and it's learned it itself. We've not said, if you're getting close to a wall, start turning away, as we probably would as traditional developers. If we were developing a 2D or 3D game, maybe we would explicitly program and say, hey, you know, if you're getting close to that wall, start turning the other way. If you come into a corner, start slowing down. We've not explicitly told it. These cars have learned, given the success criteria we've told it and reinforcement learning, that that's what it needs to do to be able to pass on its learnings to future generations. So the answer to the question we had earlier was, yes, we can create the evolving and improving learning agents to solve problems using reinforcement learning. And it's quite simple. I say relatively simple. That it's also worth mentioning that I'm probably aware that the way that John's done it, he's obviously written this code from scratch to be able to program a neural network from scratch, the learning agents from scratch, the simulation engine from scratch. I imagine, I'm fairly certain that places like Unity and other places will have packages that you can readily pull in, and it will be able to train learning agents for you. But the code that John's written is a really good starting point if you want to really look at how the underlying thing kind of stuff works. And the next thing that I wanted to do is, that's the old track. What I want to do is, this is a new track I've designed. I should probably work for Formula 1 or someone like that. I've added a lot more bends, a lot more interesting turns, and I wanted to see if we take the brain, or all those numbers, if you remember, or the neural network from the car that managed successfully get all the way around the track, and put it in a car and give it this track to go around to see if it could actually navigate it. Now, I'm ashamed to say I've not yet successfully been able to do that. So sorry for the anticlimax, but I put that down to my lack of understanding in the Unity tooling. Perhaps I've made some of the bends slightly more sharper than what they are in the original track, but I've not yet got a car to navigate the new track based on the learning from the old tracks. Hopefully one day I'll give it a bit more time, I'll be able to do that. But the theory is sound. I mean, when they train Teslas to drive on a road in America, then it's not going to be able to not drive on a similar road in a different state. Do you know what I mean? So the theory is it should work. I don't know what I'm doing wrong. Okay. And then before I start wrapping up, I just want to talk about some real life reinforcement learning applications, because this was a very sort of throwaway example, but I've seen examples of, or heard of scenarios where people are creating self-learning trading bots where they're performing automated stock trades, and then they're looking back and saying it themselves, not an external person, and saying, oh, that resulted in a loss, not a profit. I'll do less of them sorts of trades. So it updates its neural network, and it will do less of those trades in future. Conversely, if it resulted in a profit, it would say, oh, do more trades like that, because that was successful. Okay. We're also seeing more and more medicines and drugs being discovered via artificial intelligence through machine learning agents. Often these are through not methods, but combinations of substances in different quantities that it might not have even occurred to medical researchers to try, but these learning agents are doing this automatically, testing drugs against things like diseased tissue, seeing if it works, trying more of it, trying less of things that don't work. So seeing healthcare advances accelerating due to use of these sort of reinforcement learning and AI. We're also seeing things like data centers using machine learning and artificial intelligence to discover the best times to sort of cool down their data centers without using too much energy. And that's all done automatically as well. No one's programming it when to come on and when to turn off. It's kind of learning how to do that to be as efficient as possible.